Our project focused on two basic tracking mechanisms to identify phases of gait. Gait is a person's manner of walking. A person's gait is made up of two primary phases, the stance phase and the swing phase. The stance phase is when the leg being observed is leading, and the swing phase is when that leg is not the leading driver of walking. In our code, we analyzed gait to identify the angle the person's foot made with the ground, distinctions between gait cycles, and gait speed. That is, the amount of time the user spends in the gait cycle. Analyzing a person's gait can offer significant diagnostic and preventative advantages. Improper gait can have implications for mobility, flexibility, and functional strength. For example, having access to gait angle and how that changes over a person's gait cycle can help identify an improper gait. Gait disorders are highly common in most of the world's population and are key symptoms in many neurodegenerative diseases. Multiple sclerosis patients show several gait alterations, such as shorter steps, lower walking speed, higher cadence than subjects without MS. Accurate knowledge of gait characteristics can help allow for earlier diagnosis of such diseases. Our input video was a video of Chad walking. He wore two colored bands, one red and one turquoise, to identify where his heel and toes were. Our first method of tracking was a manual GUI code that allowed the user to exercise control over the tracking of the heel and toe points. In this case, the color bands would not be necessary. The second was an automated tracking system that prompted the user to select the initial lock-on points for the heel and toe, then used color data and assumptions about walking to track the rest of the movement. Regardless of which mechanism of tracking was used, once the coordinate points of the foot had been determined, these were correlated to angle and distance algorithms, which distinguished between these gait cycles, returned the angle of the user's foot, and the gait speed of the individual. Using the GUI code, the user could customize how many frames they wanted to analyze by setting how many frames to skip between selection of points. The user can also see the previous points they selected to help visualize the gait cycle and have an indication of when a certain point is generally stationary. The GUI code outputs the frame number at which the point was selected along with its corresponding X pixel and Y pixel value. These are used in calculations applied in the gait analysis code. Using the automated code, the user selects the initial heel and toe points. The code then stores this information, including the pixel locations and the RGB data values of the starting points. This RGB data is valuable because it allowed us to set threshold values to detect where these points moved in the future. The user can watch the tracking video and decide if the tracking is sufficient or if they want to reselect their initial points, which correspondingly will alter the threshold values. Both tracking methods ultimately were very similar in accuracy. However, the manual GUI tracking code had a slight edge over the automated tracking in terms of accuracy.